All right. Here's a question for you. Tell your neighbor.
Balance forces or it would be really unbalanced forces means that exactly. Yeah. So,
Is it next?
Okay. What do you think? All right. So, is inertia doing what it wants to do? No. Inertia wants to maintain a constant speed in moving in the same direction. Have a constant velocity. This is not a constant velocity. Okay? So, there has to be an unbalanced force. Does that make sense? To make inertia do what it doesn't want to do. Now, looking at work, this is a different perspective. This is why. Work is a process, not an instant. So far we've been like when we're doing free body diagrams, it's a snapshot. Like, hey, what forces are acting on the object right here, right now? Work, it looks at a process going. So you have to define, hey, what's your initial and what's your final starting conditions? Okay. So initially we're going this way at 60 miles an hour. We're slowing down. Is friction, the brakes from the friction is doing positive or negative work? Negative work. You good with that? Okay. But then we turn around and we speed back up. Is the engine doing positive or negative work? It is now doing positive work. Okay. But by the time we're back up to 60 miles an hour, does kinetic energy have direction? Kinetic energy does not, it's 1/2 mass times speed, not velocity, but speed squared. Okay? So the fact that we're going this way, first and then this way next doesn't make a difference. So if we start here 60 miles an hour and we end here going 60 miles an hour, there has been no change in kinetic energy from this point to this point. That process, the overall process, the net work was 0. How's that possible? Because the negative work done by the brakes, by friction, is added to the positive work done by the engine. So at the end of the day, at the end of that story, the net work was 0. If I just looked at the slowing down process and we started at 60 miles an hour going here to rest, that process would have a negative work. If we started here at rest and got to here 60 miles an hour going this way, then that process would have positive work. But if I start here 60 miles an hour and end here at 60 miles an hour, the net work of that entire process is 0. Do we see the difference? It's not a snapshot. You have to define, here's my starting point, here's my ending point. Okay? That is a really big difference between what we've been doing up until this point and then when we're talking about working energy. Okay? All right, give this one a shot. Thumbs up when you have a guess. Okay, for the sake of time, gravity, the FGX, that's doing positive work. Normal force is 0 because it's acting perpendicular. Friction is doing negative work. It's speeding up, so your change in kinetic energy is positive, meaning that your net work is also positive. B. Okay. Your natural force is 0 because it's acting perpendicular. Good with that? Alex?
Natural force is always 0.
Not always, but often it is. An elevator would be an example. Riding in an elevator would be an example where it'd be doing positive work if it's going up or
If it's, as it's going down, if it's faster.
while it's going up, positive, as it's going down, negative. So positive, negative, positive, negative, positive, negative. Okay. See? Okay. Correct answer is E, 4 times. Hopefully you saw that from your lab. Okay. When you double the speed, you have to square that. That becomes 4 times. Good with that? 4 times your kinetic energy. So, the consequence to that, you're going twice the speed. Correct answer is 4 times the distance. Okay? Hopefully your lab demonstrated that. Theoretically, that's what it should have been. 4 times the distance when you double the speed. Why? Because your kinetic energy is squared. Sorry, the speed in kinetic energy is squared. You okay with that? Okay, that's huge. That is not intuitive. Most everybody thinks, oh, twice the speed, twice the distance. Okay, one year when we were studying this, we had an early snow, and they're like, prove it. Like,
Check.
okay.
10 miles an hour ain't good. Jump out front of me.
Okay, so you're going 10 miles an hour. Let's get it that far.
Wait, are you measuring the year there, Matt?
Yeah, from wherever like that. The red number
20 miles an hour.
Okay, so twice the speed. Four times the distance. Crazy, what? Okay, now, folks, this is the best slide I could find. As we approach into the wintry months, it's really important that you recognize some stuff. Okay, first off, just on normal conditions, twice the speed, 4 times the distance. That is not intuitive. Okay, all I could find is going from 30 miles an hour to 50 miles an hour. Okay, and this incorporates the reaction time, like, oh shoot, I need to stop. So like the time it takes to take your foot from the gas to the brake. Okay, 30 miles an hour, it takes 12 meters to stop. Okay, doing it on snow, 2.5 times the distance, like 30 meters. If you're on ice, over 5 times. That's at 30 miles an hour. Okay, we're not going to double, we're just going to 50 miles an hour. Notice how much further you're going. Okay, if you're on ice, going 50 miles an hour, that's close to a quarter mile. Okay, if you see someone's brake lights and you're going 50 miles an hour on ice, you're going to hit them because that's a quarter mile away.
I have a question. In the video, like to stop, you didn't use your brakes, did you?